Motion modeling refers to the problem of finding a robust, concrete, and expressive pose representation. Motion is highly influenced by the skeletal attributes of characters and may appear differently on characters with different proportions. Over the years, much effort has been devoted on the design of complex architectures and learning schemes which properly capture high frequencies of motion. However, less effort has been dedicated to the motion parameterization, even though it is of equal significance. Existing work models motion using either positional or rotational representations. Positional representations do not contain orientation information, causing abnormal rotation around the limbs when rotations are recovered. Commonly used rotational representations, such as Euler angles, are discontinuous, resulting in unnatural motion while being prone to error accumulation along the rig. That is why most recent deep learning architectures parameterize motion using local rotations and then employ a forward kinematics layer to recover current positions. The positions are then used as a constraint, accounting for the error accumulation. In this work, we present a hierarchical motion representation based on dual quaternions, which can encode prior skeletal information by simultaneously describing current displacements and rotations in a root-centered manner. To evaluate the performance of our representation, we incorporate it into two state-of-the-art networks, namely the ACRNN and the quaternet. First, we demonstrate the effect of the antibodal property, which is evident in the form of absurd flickering on the joints of the green character. Here we show the ambiguity on the orientation about the roll axis when the positional representation is used. Note the abnormal rotation around the limbs present on the brown skeleton. Our representation in purple overcomes this limitation while preserving the quality of the generated motion. Next, we assess the learning and convergence of various representations using the same laws at different training stages. With 30,000 iterations, the motion generated with quaternions in blue and ortho-60 in orange present artifacts. Note the shaky motion of the blue and orange characters. On the other hand, these are not evident with our representation. With 150,000 training iterations, we observe that the artifacts present when using the ortho-60 and quaternions get reduced. However, note that some abnormal motion is still present in the blue and orange characters that is not reflected in ours. We further examine the ability of our representation and others in synthesizing long-term sequences of complex motion. The generated motion does not freeze for any of the representations. However, it gets repetitive. Compared to the other representations, motion generated with ours is more natural and stable. For quaternions, we additionally evaluate the performance of different variants. The light blue skeleton on the right, which shows the quaternions with appended positions, is shaky, while the one on the left, which represents a quaternion variant with an FK layer, generates the motion with the fewest artifacts. We conduct an ablation study to evaluate the contribution of each of the proposed losses of our representation. This video shows that while all variants produce motion of equal quality, the use of MSC loss alone is sufficient. Having identified the best variants of quaternion-based, ortho-60 and dual quaternion representations, we compare them together. We observe that even though the artifacts present when using other representations are less significant, they are not evident in motion generated using our representation. The second experiment employs the quaternet. In this example, we show results of our motion representation in purple and the original quaternet architecture in green that receives unit quaternions, employs forward kinematics to recover the position, and constrains the motion with a positional loss. When we do not incorporate forward kinematics on the quaternion, the motion is uncontrolled and presents artifacts at certain points. Our representation encodes features of motion correlated with the skeleton configuration, allowing for training on databases containing skeletons with different proportions without the need for retargeting. Here we can see the results of unseen motion on seen characters. The ground truth motion is shown in green, motion generated with quaternion offsets representation in blue, with ortho-60 offsets in orange, and ours in purple. Note the jittery motion of the blue and orange groups. In this example, we assess the scenario of seen motion on unseen character. The motion generated using our representation more closely resembles the reference motion. Finally, for the case of unseen motion and unseen character, it can be observed that our representation adapts the generated motion to the character better than the other representations. Thank you.